Okay, so I ask that you bear with me during this page. We would have a lot of back and forth if we were actually in the classroom on this page, so I could ask you many different questions. I'm going to try to do that through the video, but it might be a little more difficult to kind of get that discussion through the video, but I'm going to try. So let's start going here. It says, in a normal distribution shown below, the area of the shaded region is 0.159 units. So that's that red shaded area in this picture. It says that region represents the fact that 15.9% of the data values were greater than or equal to 10, because the area under the curve is 1. The unshaded region has the curve area of 1 minus 0.0159, which is 0.841. So all it's saying is we know that entire curve represents 100%. The pink area represents 15.9%, so the white area beneath the curve, the unshaded region, has to represent the rest. So what's 100 minus 15.9? That's 84.1%. So this is all they're doing, is they're just saying that this part right here is the 84.1%, and this part right here is the 15.9%. That's all they're saying right there, so don't get confused. It says the following is called the empirical rule. It's really important that you know the empirical rule because we will be using the empirical rule to solve a few problems. In fact, it will directly state in the problem, using the empirical rule, solve the following. And it's really important that you use this rule because we are going to learn 2 ways to do problems. Okay? So I just want you to write some notes here. When are we going to use the empirical rule? Well, first of all, you're going to use it when it says to use it. But we can only use it when your z-score is an exact standard deviation. Okay? So if you remember z-scores were how far am I away from the curve in terms of standard deviations. Okay? Standard deviation was just a distance from the mean. If you remember, it's how close is everything to the middle. That's what a standard deviation is. So a standard deviation is a measure of saying how far is everything spread. So I told you the vast majority of data lie within 1 standard deviation of the mean. And then I said even more lie within 2 and even more lie within 3. Well, the empirical rule tells us exactly how many data is there as long as it's normally distributed. Again, we're assuming everything is normally distributed. So if I told you your z-score was 1, -1, 2, -2, 3, or -3, then we can use the empirical rule. But anytime you have a z-score that is not an exact deviation, for instance, if my z-score is a 1.2, where I'm not exactly 1 standard deviation above the mean, this empirical rule means nothing. So the empirical rule only works for scores that are exact standard deviations away, plus or minus 1, plus or minus 2, plus or minus 3. So what does it say? Well, in my previous one, what I was trying to do is I overestimated, and the reason I overestimated was just to try to give you guys some context. Anytime I gave you a data set, for instance, I might have said test scores, I might have said the average test score was a 75, and the standard deviation was a 5. So what I told you to do is write a number line, mark 75, and then I said, what do you do? Well, you add and subtract that standard deviation, so you would have 80 and 70, and I said the vast majority of test scores were between a 70 and an 80, and I said something like 80%. Well, that was an overestimate. It's not 80%. What the empirical rule states is as long as it's normally distributed, the amount that lies between 1 standard deviation of the data is 68%. So we know that 68% of the people who took the test, as long as it was normally distributed, got scores between a 70 and an 80. Just take that mean. Mean is 75. Let me write that down so you know. The mean I'm saying here is 75. The mean test score was a 75, and I'm telling you that the standard deviation, I don't care, we can use the population standard deviation, doesn't matter. I'm just going to write SD for standard deviation, was 5. So this is what it would look like. If I took the mean, I added 5 and subtracted 5, I'd have 68% of the people. Well, what would be next? Add another 5 and subtract another 5. I'd have an 85 and a 65 would be my test scores. So the question becomes, how many people scored between a 65 and an 85 on the test? Well, the empirical rule says 95% of people score within 2 standard deviations of the mean. So that would represent 95% of those students who took the test scored between a 65 and an 85. And then let's go on even one further. If we add another 5 and subtract another 5, which would be a 90 and a 60. So if I extended my little chart right there, what does the empirical rule say? The empirical rule says that 99.7% of the people scored between a 60 and a 90 on that test, given that the mean was 75, the standard deviation was 5, and it was normally distributed. So if you notice that's not quite 100%, what does that leave? It leaves a very small bit for outliers. So maybe some students got a higher A on the test, and maybe some students failed that test, but that would be very, very, very small percentage of the population in this case. So that's what the empirical rule is. 68% lie within 1 standard deviation, the range of 1 standard deviation. 95% lie within the range of 2 standard deviations, and 99.7% lie within 3 standard deviations. But now what I want you to do is I want you to think back what percentage of think back to what it means to be normal. It means the exact same area or amount are to the right of the mean as it is to the left of the mean. So I want you to understand how they got this next chart. So I'm going to go back to the red here, the scores from 70 to 80. And I know that the entire thing of 1 standard deviation is 68%. So what happens if I do 68 divided by 2? Well, 68 divided by 2 is 34. So what does that mean? That means 34%, because it has to be the same on the left and the same on the right, 34% would lie between 70 to 75, and 34% would lie between 75 and 80. And so if you look at that, that's exactly what they're showing in this chart over here, is they're showing this shaded region that I just shaded, that red region right there, has to be 34%, because the other 34% lie just to the right of it. Okay, this chart, you guys get 1 note card on your test. This chart is exactly what I'd be putting on my note card, except I'm going to add 1 little bit to this chart that's not there that's going to help you out big time. Okay, so let's think, how in the heck did they get the next one? Well, let's look at the next one. Again, we have the same amount must be to the left of the mean as the right of the mean. So let's look at 95% and divide that by 2. If you do 95 divided by 2, you should get 47.5. So what are we saying? We're saying this entire area, I'm gonna use my laser pointer, from 75 to 85, that would be 47.5% of the data. But we already know that 34% are between 75 and 80. So the question becomes, how much is there between 80 and 85? Let me say that again. 47.5% have to be between 75 and 85. But we know that 34% are between 75 and 80. So the way that we find the amount from 80 to 85 is we subtract 47.5%, what the whole thing has to be, minus the 34%, which is the 75 to 80, and that gives us 13.5%. So 13.5% of the people scored between an 80 and 85. That's exactly what you see in what's now the shaded region of that next one. There's my 13.5%. That would be the data scores from 80 to 85. Likewise, we can do the same math for the last one. So if we do the 99.7 divided by 2, if I do 99.7 divided by 2, I'm getting 49.85. So 49.85 would be all scores from 75 to 90. Again, 49.85 would be all scores from 75 to 90. But I want to know how many scored just between 85 and 90. So how am I going to do that? I'm going to do 49.5%. I'm going to subtract off the 13.5% that's from 80 to 85. And I'm going to subtract off the 34% that's from 75 to 80. Sorry, quick typo here, so let me erase this. It's not 49.5, it's 49.85. So I do 49.85 minus the 13.5 minus the 34. When I do that, see what you're getting? I'm getting a total of 2.35%. So that means 2.35% of the people on this exam, in this situation, would have scored between an 85 and a 90. Well, again, this is symmetric, so that also means that 2.35% have to score between a 60 and a 65, and we also know that 13.5% had to score between a 65 and a 70. So that gives us our percentages. But here's the question: how many scored above a 90 and how many scored below a 60? That is the one thing that is not given to us on this exam, or on this picture over here. They have every single one of those labels regioned for us, or regions labeled for us, except for the last region. So I'm going to color this last region in blue. I'm talking about just those tail ends, just those outliers. How much would be left? Well, if everything between, let me go back to the test scores because I think this will make more sense. We know everything between 60 and 90% is 99.7%. So what's the only thing that's left? Well, what happens if you do 100 minus that 99.7%? I'm getting 0.3%. So 0.3% is left for the outliers. But again, we have to have just as much on top as we do on bottom. So what I have to do is that 0.3, and I have to divide that by 2. If I do 0.3 divided by 2, I end up with 0.15. So what percent lies above 90 would be 0.15%, and what percent lies below 60 would also be 0.15%. Okay? Let me put those percentages there. So this chart is exactly what I'd be putting on my note card, except I want to add in those tail ends of 0.15% and 0.15% on the bottom as well. Those are very, very, very important, okay? Let's see why. Now that I have this chart right here, I could answer all sorts of questions. For instance, if I said, what percentage of students scored above 80%? Let me go ahead and write this down for you. How many scored above 80%? Well, now that I've labeled all of these regions, it's very, very easy. All I have to do is look to the right of 80. If I look to the right of 80, I would have 13.5 plus the 2.35, and then the chart doesn't show it, but you have to remember it. That tail end is the 0.15. So if I said how many scored above an 80%, in other words, how many students got a B or above on this test, 13.5 plus 2.35 plus 0.15, I'm getting 16% scored above an 80 on the test. What if question 2 said how many scored between 65% and 75%? How many scored between 65% and 75%? We'll just go and look at the areas that we've already labeled, and you would see that we would do 13.5 plus 34. If I do 13.5 plus 34, 13.5 plus 34, I'm getting 47.5%. Let's do another problem. If I said how many scored below, I don't know, how about below a 65? How many scored below 65%? Or no, let's change that. Let's say how many scored below 60%. So that would represent how many students failed this exam, right? A 60% is a D. So how many scored below 60%? Well, just look at the graph. It's 0.15% of the people scored below a 60%. So what could you do? Now that you have the percentages, if I told you how many students took the exam, you could calculate the number. So for instance, if 100 students took the exam, 16% of 100 is 16. You could say 16 students got a B or higher. You could say 47.5, which doesn't really make sense. So you could say either 47 or 48 students scored between a 65 and a 75% of the exam. And you could say 15 students scored an F on the exam, or 15 students failed the exam. That's presuming that 100 students took the exam. If 200 students took the exam, you would just take that percentage and multiply it times 200. That would give you your quantity. Remember, these answers are in terms of decimals or percentages. But this is the chart that I really, really want you guys to know. This is the chart that would be, without a doubt, on my note card. I'd be looking at this chart. It's really easy to get the actual tick marks on your axis. The tick marks on your axis are the only thing that are going to change. The 68%, 95%, 99.7%, all those percentages on the top are always going to be the same. You always start in the middle, which is the mean, and then you just add and subtract the standard deviation from each one of those scores.